In this video, I'd like to talk about the math question of the day for Saturday, July 8th, 2023. And with this problem, we need to use L'Hopital's rule to evaluate this limit here, this quotient where we let z approach 0. And L'Hopital's rule is typically taught in a Calculus 1 class. So at this point, go ahead and pause the video, see if you can work through this problem on your own. And when you're ready, unpause the video and we can go through this together. Now, assuming that you have attempted the problem, let's start working through this. And as a reminder, we can say that L'Hopital's rule is simply when we take some limit as, let's say, x approaches some value a of, we have a quotient here, f of x over g of x, we can apply L'Hopital's rule if, when evaluating this limit, we end up with an indeterminate form. Let's say 0 divided by 0, or maybe it's infinity over infinity, or something like that. There are several indeterminate forms. And if when we plug in this value of a to our functions in the numerator and denominator and we get an indeterminate form, we can use L'Hopital's rule, which says that this limit is equal to the limit as x approaches a of the derivatives of each of these functions, f prime of x divided by g prime of x. So if we plug in 0 to our function here, this quotient, and we get that indeterminate form in our numerator and denominator, then we can take the derivative of the top and the derivative of the bottom and then just evaluate that limit again. Now, sometimes you need to apply L'Hopital's rule several different times. So if we get another indeterminate form after taking the derivatives and plugging in the z value of 0, then we can just apply L'Hopital's rule again and repeat the process. Plug it back in and see if we still get an indeterminate form or if we actually get back some type of answer. So we can start by just plugging in z is equal to 0. And we'll get the sine of 0, which is 0. And then each of these terms will be 0. And in our denominator, we get z squared, or 0 squared, which is 0. And we get 0 plus 1 on the inside, which of course is just 1. And notice that we get 0 in the numerator and in the denominator after everything simplifies. And like I mentioned, this is an indeterminate form. So from here, we can apply L'Hopital's rule by taking the derivative of the numerator and of the denominator. So let's rewrite. We have the limit as z goes towards 0. Now we take the derivative, and the derivative of the sine function, we'll have to use the chain rule as well. But the derivative of the outer function, which is the sine function, is the cosine function. We rewrite the inner function, then we multiply by the derivative of that inner function, which would be 2. We just use the power rule there. Then we use the power rule for these terms here, this quadratic and linear term. We bring down the 2 in front and multiply. 7 times 2 is 14. Then we subtract that exponent by 1, so it's z to the first. And we do the same for this linear term. We bring down the exponent, we subtract the exponent on z by 1, so that it's z to the 0, but z to the 0 is 1, so we get minus 2 times 1, which is just negative 2. Now we divide by this denominator, and it's up to you if you want to multiply this out, or we can use the product rule, since remember that if we have a product of two functions, f times g, and we take their derivative, this is equal to the derivative of the first function multiplied by the second function, plus the derivative of the second function multiplied by the first function. So let's apply that here. We take the derivative of the first function, which would be 2z. We multiply it by the second function, which is z plus 1 squared. Then we add the derivative of the second function, which will use the chain rule. The outer function is the square function, so we bring the 2 down in front. We use the power rule. We rewrite that inner function. And then we multiply by the derivative of the inner function, but that would just be 1. since the derivative of a constant is 0 and the derivative of this term, we use the power rule, we bring the 1 down in front, 1 times 1 is 1, and we have z to the 0 since we subtract that exponent, and z to the 0 is 1. So that we are just multiplying by the derivative of this, which of course is just multiplying by 1, so that doesn't change anything. And then we multiply by that first function, which we know is z squared. And at this point, we can try plugging in our z value of 0 and seeing if we get an indeterminate form or if this actually evaluates to something. So let's plug in z is equal to 0 here. We get the cosine of 0, which is 1, and 1 times 2 is 2. Then we get 14 times 0, which is 0, and we subtract 2 from that. So our numerator will be 0. But our denominator, we can plug in 0 now, and we will get 0 multiplied by 1 here, and we get plus 2 times by 1 times by 0. So we do actually end up with 0 over 0 again, which is indeterminate, which means that we will have to apply L'Hopital's rule once more. And hopefully from there we can actually evaluate this. So applying L'Hopital's rule again, we still have this limit as z goes to 0, and we take the derivative of our numerator and of this denominator. So in the numerator, we have this 2 that will just carry along, and we multiply by the derivative of this outer function, the cosine function, which is the negative sine function. We just rewrite that input, and then multiply by the derivative of the inside, which is 2. Here we use the power rule, we bring this exponent down in front, 1 times 14 is 14, and we get multiplication by z to the 0 power, which is just 1, and we know the derivative of a constant is 0. So this is our new numerator after taking the derivative of this one. And for our denominator, we again have the choice of multiplying everything out, or we can just use the product rule again, and we'll have to use it twice here, so it gets a little bit tedious. So it's up to you if you want to just multiply all this out. But let's use the product rule to practice that. And when we look at this first term here, we do the derivative of the first function, which is 2, multiplied by the second function, z plus 1 squared. Then we add the derivative of this second function. We bring the 2 down in front, subtract the exponent by 1, multiplied by the derivative of the inner function, but the derivative of z plus 1, we know it's just 1. And then we multiply by the first function. Then we add the derivative of this term here. And again, we can use that power rule. We have the derivative of this first function, and let me just distribute this too. We get 2z plus 2 multiplied by z squared here. And really, this one, since we don't have an exponent here on the parentheses term, this would probably be easier just to multiply out. So multiplied out, this is 2z cubed plus 2z squared. So now we can just use the power rule here. We bring the 3 down, we get 6z, and subtract the exponent by 1, so 6z squared. And for this term, we bring the 2 down, we get 4 multiplied by z and to the first power. So this right here now is our new denominator. And let's now plug in a z value of 0 to see if we get an indeterminate form or if this actually evaluates. In our numerator, we get twice the negative sign of 2z, or 2 times 0, but the sign of 0 is 0. So this first term is just 0. 2 times 0 times by 2 is 0. Then we add 14, that is addition by 14. So our numerator is just 14. And in our denominator, we get 2 multiplied by 0 plus 1, which is 1. We square that, and 1 squared is still 1. Then we add 2 times by 1 times by 0, but 2 times 0 is 0, so we're adding 0 there. And each of these terms will be 0 as well. So our numerator is 14, and our denominator is 2, and all of this simplifies to 7. And since we were able to find an actual answer here. This is the answer to our original question. This limit is simply equal to 7.